Hello everyone. Today's session is the continuation on indeterminate forms and LHopital's rule. In the previous video session, I talked about the indeterminate forms of the kind 0 by 0 and infinity by infinity. Now there are other forms also, such as 0 times infinity, 1 to the power infinity, infinity to the power 0, 0 to the power 0, and infinity minus infinity. Now, if we have expressions of these forms, the idea to solve these indeterminate forms is to convert each of these forms to either 0 by 0 or infinity by infinity, because the LHopital's rule can only apply to indeterminate forms of these kinds. Now, the indeterminate forms of the kind 1 to infinity, infinity to 0, or 0 to 0, they arise from limit of functions that have variable bases and variable exponents. We will see them as examples later on. Now let's look at some examples which lead to the indeterminate form 0 to infinity. First one, now if you just look at this limit, as x approaches to 0, 1 is simply 1. But if I write this by 1 by x, so it's infinity times 0. Similarly, limit as x approaches 0, 2 over x times x is the same as 0 times infinity. Now, third example, limit as x tends to infinity, 1 over e to the power x. So it's 1 over infinity, which is 0, times x, here infinity. Or we can have an example as limit as x tends to infinity, 1 over x, which is infinity. 1 over x, basically 1 over infinity, 0, times e to the power infinity is infinity. So all these four are examples of 0 to infinity. Let's look at an example and see how we can play with these terms and change it to the terms of 0 by 0 or infinity by infinity. So here's the example. Limit as x tends to infinity, e to the power minus x times square root of x. So when we look at it first, so this means this is e to the power negative infinity, okay, and times infinity. So when this is e to the power negative infinity is 1 over e to the power infinity times infinity, this is 1 over a very big number, which is basically 0 times infinity. Okay, so we have a 0 by infinity. Now, how can I rewrite this expression so that I get the form either 0 by 0 of infinity by infinity? Okay, so if you write this expression as take e to the power minus x in the denominator, which becomes e to the power x. So now what we have is infinity over e to the infinity, infinity over infinity. So clearly, we can apply LHopital's rule. So when you take the limit as x tends to infinity, so this is the LHopital's rule. Now first we're going to change, so we're writing it in this form. Keep this in mind. We're writing it like this. And then we do because if we do the infinity by infinity, we apply the LHopital's rule, it's not going to work because remember, it's a product of functions. So it should be here. So this one, I would say I've missed a step. So this actually goes over here, and from here, I go and apply the infinity over infinity. So this is first changed to this, and then the equal to here is the LHopital's rule. Remember, you do not apply LHopital's rule to this expression because you cannot do so. You can do it when you change the way it looks. So that was my little mistake. I forgot to do it. So here's the one. So from this expression, you go to this. Then on this expression, you apply the LHopital's rule. And e to the power x is e to the power x. And square root of x is 1 over 2 square root of x. That's a differential. Now, we can write this as 1 over 2 square root of x e to the power x, which when you substitute x inside here, it's 1 over 2 times infinity, it is 0. Pretty simple here. Okay, now let's look at an example of the form (1 over infinity). That's an indeterminate form. Okay, now let's see this one. Now remember, we talked about these are the forms where you have some, variable exponents kind of scenarios. Your exponents are variables. So clearly my exponent is a variable here. So in this scenario, when I substitute, so this problem, let's look at this one. Limit as x tends to infinity, 1 plus 1 over x to the power x, a variable exponent. So when I substitute infinity in this expression, I get 1 plus 0 to the power infinity. So clearly, I have an indeterminate form. So what is the rule? We change it to the form of 0 by 0, infinity by infinity. Now to solve these problems, you have to think a little carefully. The reason is I'm going to have a variable as in my exponent. So I would like to kind of remove this variability in a form which makes my life simple. So what I'm going to do is, I'm going to say, we assume with that the limit is existing. Okay? And then we say, suppose the limit exists and it is equal to 1. So we get this expression. Now I take the natural log, because with the natural log, this x can be bumped out because of the properties. Remember that. Okay? Now when we take the natural log of each on each side of this equation, we get natural log of y, natural log of all this expression. This whole limit comes down. Now remember, my natural log is a continuous function, so natural log can go in. And that's the most important key point. And when you get the forms of 1 to infinity, this is one of the best techniques to play with. Okay, notice. Now, because my natural log is continuous, I can take the natural log inside and the limit comes out. So the limit as x tends to infinity is now natural log of 1 plus 1 over x to the power x. Now we apply the properties of natural logs. So the x comes out, natural log of 1 plus 1 over x. Now this, notice. So when I substitute, so this one, when I put infinity, so it's infinity over natural log of 1. So this is infinity times 0 because x is infinity, natural log of 1 is 0. Now we have to once again change this looking of infinity times 0 to something of a 0 by 0 or infinity by infinity. We can't do anything on the natural log. But this x, this is the same as x over 1. So when I take in the denominator, so if I take this down, pull this down as 1 over x, because when I remove the division sign, it becomes x over 1. So that's the little trick here. Now, limit as x tends to infinity of natural log of 1 plus 1 over x over 1 over x. Now when we do it, what is it? This is a 0 over 1 over infinity, a 0 by 0. Now, my LHopital's rule can be applied. So notice till this point, we were playing with little algebra here. We're doing this little tricks we learned in the log properties here. Okay, so let's go ahead and do the differential of 1 over x, which is minus 1 over x squared. And differential over natural log of 1 plus 1 over x is 1 over 1 plus x. And you take the differential. Now remember, this is chain rule, guys. So you take the differential of 1 plus 1 over x, which is again minus 1 over x squared. Now this is clearly, you notice this expression in the numerator and denominator cancels out. What are we left with? Limit x tends to infinity 1 over 1 plus x. And then when we substitute in the infinite term here, what do we get? Limits to infinity here. So 1 over infinity, that's 0, 1 is the answer. But remember, we're not yet done because this is natural log of y to be 1. And we have to find y. Remember, this is what we're looking at. This is the expression we want to finally get. What we have got is natural log of y is 1. I want to get y. And how do we get it? Exponentiate the whole equation. So y is e to the power 1. And that's the answer. So that means the limit of x tends to infinity, 1 plus 1 over x is e. And that's what I've done in this slide. Okay, now let's look at another indeterminate form. This time, we'll be looking at the indeterminate form of the kind 0 by 0. And I'm also going to take a one-sided limit. So limit as x approaches 0 positive of sine x over x. So when x approaches 0 positive, that's the right-hand side, sine of 0 is 0, 0 to the power 0. Clearly, we can't apply the LHopital's rule. We again have to do some game here. And the way to do it is that, remember, if you have 1 to infinity, 0 to 0, those kind of problems, we need to, this is the best way I normally see. When I say let y be the limit for this one, and we assume it is existing, okay? So y equals limit x approaches 0 positive of sine x over x, and then take the natural logs on both the sides. Natural log of y equals natural log of limit of sine x over x. And as we did in the previous example, we're going to say, not going to say, but it is the truth, is like here, the natural log is continuous. So that means this natural log goes inside. So what do we get here? So we're going to get limit x approaches 0 positive, that's the right-hand side, natural log of sine x to the power x. So now you apply the natural log properties. It is x times natural log of sine x. Now once again notice, now if you want to apply the limit, what do I get? I get a 0, natural log of 0, infinity. Remember the graph of a natural log function? As you get closer and closer to 0, it goes down, 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 down here. Do you see this one? So it's 0 times infinity. So it's going to negative infinity. But it's a 0 times infinity, in other words here. Okay. So what do we do? So look at this one. We can't do anything to natural log. But here we can play with this little x. And we rearrange this expression as natural log of sine x over 1 over x. And now this expression, natural log of 0, you have a negative infinity. Oh, sorry, it was 0. Sorry, guys, I was not. Yeah, it's right here. Sorry. Natural log, that's natural log of 0 positive. So it's negative infinity over 1 over 0 as a positive infinity. So we can still apply LHopital's rule here. Okay, so the limit as x approaches 0 positive, natural log of sine x. Now remember, it is 1 over sine x times the differential of sine is cosine x, which is cotangent x. So limit as x approaches 0 positive, cotangent x over minus 1 over x squared. Now we have to see if we can apply, so let's say 0, cotangent 0. Kind of not working, but if I rearrange the statement, so it's minus x squared over tangent x. Because the tangent of 0 is 0 and x squared is 0. So now this is a 0 by 0 form. So once again, I can apply my LHopital's rule. Remember, negative infinity to infinity. So you apply, you change this way it looks so that it becomes a 0 by 0 form. And you take the differentials, that is again negative 2x over secant square x, now secant of 0, which is basically 1 over cosine 0. This is important to keep in mind, which is 1 over cosine 0, guys, the whole square, and 1 over cosine 0 is 1, so it's 1, and it's minus 2 times 0 is 0. So the answer is 0. Because anything multiplied to 0 is 0, negative that kind of doesn't work there. Okay, so now notice this was the expression, natural log of y is 0. Okay, so we get this expression, natural log of y to be 0, or y is e to the power 0, or 1. So this answer, limit as x approaches 0 positive of sin x over x is 1. And that's what is in this slide. Okay, now I'm going to look at one more indeterminate form. Infinity minus infinity. Okay, look at the way when I do these problems, keep this thing in mind, is that I'm using very special ways of playing around with it. Sometimes I have to, change the way the expression is looking. Sometimes I have to do natural logs, all those things. Now, when you have infinity minus infinity, so we need to, as usual, so an expression here, limit as x approaches 1 positive, 1 over natural log x. Natural log of 1 is 0, so 1 over 0 is infinity here, minus 1 over, again, 0, which is infinity. Now, this one is not going to be work if I straightforward apply LHopitals, but we need to change it to this form. To do that, and I cannot use y equals this and take the natural log, because this is not going to work over here. We don't have some variable exponent here. But we see if we play a different role. We have two expressions. Let's combine these two expressions into one expression. Okay, so we say limit as x approaches 1 positive is x minus 1 times natural log of x, and it's x minus 1 minus natural log of x. Now let's go ahead and substitute 1. So it's 1 minus 1 minus natural log of 1. Remember, natural log of 1, guys, please keep in mind, is 0. So 1 minus 1 minus 0, so it's a 0. And clearly, denominator is also 0. So we have a 0 by 0 form. So we can definitely apply the, now over here, because it's 0 by 0, we can apply our, oh, sorry, this is not needed. Okay, so we now apply the LHopitals rule, because this is 0 by 0. LHopitals rule, so x is 1 minus 1 over x, and now remember there's going to be a product rule. It's two expressions, x minus 1 times 1 over x plus differential of x minus 1 times natural log of x. Okay, now once again when I substitute 1, what do I get? A 0 on the top and a 0 in the denominator. So once again I apply my LHopitals rule. So the differential of 1 minus 1 over x. Okay. Give me a second, guys. Okay, guys. So here's, I missed a step, so let me talk about that, because when I'm going to go ahead and apply the differential over differential here, what's going to happen is that I will again get squares and stuff like that. But let's rearrange the statement, okay? Let's look at this problem, this function, sorry. And I'm going to rearrange this. I'm going to write it over here. This is going to be x minus 1 over x times x minus 1, 1 over x plus natural log of x, okay? So doing a little algebra so that I have no issues. Rather, it's a 0 by 0, but when I want to do the LHopitals rule, I'm going to have some issues. So I want to really make my life simple here. So I can rewrite this as this x can go down. I will have x minus 1, x times x minus 1 times 1 over x. Remember, it's going to multiply this whole expression plus x times natural log of x. Now, so we're going to do is limit as x tends to 1 positive, which is going to be x minus 1 over, now remember this cancels out, x minus 1 plus x times natural log of x. Yeah, I missed this step and I can see why, so we have to go this route. Now you apply the LHopitals rule, and this is what you get. The differential of x minus 1 is 1. The differential here is 1. Now, this is the product. So, plus x times 1 over x plus natural log of x. So, what do we get here? So, we are now left with limit x to the power 1 positive 1 over 1 plus 1 plus natural log of 1. Now, when x approaches 1, okay, this one is, guys, natural log of 1. No, sorry, x, sorry. So, when x approaches 1, so what is it? 1 over 1 plus 1, natural log of 1 is 0. So, your final answer is half. Okay. Now, we have talked about indeterminate forms. What about determinate forms? Well, determinate forms are the forms of the kind where the infinity plus infinity is infinity, negative infinity is negative infinity, 0 to infinity is 0, 0 to negative infinity is infinity. Remember, the LHopital's rule is applicable if you have a specific kind of an indeterminate form. Very, very important. So let me talk about those pointers. As I said, the LHopital's rule can only be applied to the quotients which lead to the indeterminate form. Now over here, for example, this is incorrect. Limit is what is e to the power 0 is what? 1 over 0. So I cannot apply LHopital's rule because this one is what? This is 0, e to the power 0, sorry, e to the power 0 is 1 over 0. So this is not the right way. Be very, very wary of it. Okay. Now, so the limit of the numerator is 1. So this is very important. The hypothesis of LHopital's rule should be satisfied. Okay. As usual, what do I tell you guys? Practice problems. So here are 3 practice problems for you to work on. And we're done with this LHopital's rule and the indeterminate forms. Thank you.